Okay, so what we're going to talk about today is making predictions in physics, and that sort of seems like, well, that's kind of an obvious thing. You make a prediction. You like, how far is it going to go, or where's it going to end up? The thing about making predictions is that it turns out that no matter what prediction you're making, you have to have some information to begin with, and if we were to look at, for example, somebody shooting a basketball into a hoop. If we were to ask, how long will it take the ball to get in the hoop? The answer is, well, it depends, right? Like, it depends. Like, somebody might, it depends on how far away they are. If you're shooting from half court, it takes longer than if you're shooting a layup. It depends on how close they are vertically. Like, when I shoot a layup, and I know many of you aren't going to believe this, but I'm not that close to the basket vertically because I can't really jump that well. But if you look at, like, your average decent high school, college, NBA player, they get a lot closer to the hoop. Sometimes they're like right there, and then they drop it or push it in. Like a slam dunk happens a lot more quickly than a free throw. So the amount of time that it takes for a ball to go from one place to a basketball hoop, assuming that the basket goes, depends. It depends on how far away the ball starts from the hoop, and it depends on like how quickly it's thrown. I mean, we don't think about it as throwing because you're shooting, but it is you're throwing. You're throwing the ball into the hoop. And in the case of most of the stuff that we're going to be doing in physics, we kind of break down the initial information into a few different categories. One is measurements. And those are things that as we are kind of starting the process of making a prediction, we simply don't know. But we can find out. And a lot of times, the way that we find out is by doing some calculations. And that's where sometimes people get confused, because if I ask a question like, how fast is the ball shot from the projectile launcher? That sort of seems like a prediction, right? Like, we're predicting, we're doing some calculations. But really what's going on is, if we want to be able to make predictions about where a ball is going to go after it's shot, first, we need to know how fast it's going. There's some other things that fall into the category of maybe what we would call givens. Those are things that you might need a measurement at some point, but you're not really measuring them to determine them. It's not illuminating, right? Like with the ball, when it's shot, we have no idea how fast it's going. We have to measure it somehow. We have to do some sort of measurement to figure out how quickly the ball is moving as it's launched. But we could say, we're going to put the ball a meter above the ground. And that would be a given. Now, how do you get it a meter above the ground? You do measure, right? You have to put the ball somewhere, and then you take a meter stick and you verify. But it's a little bit different to say, I plan to put the ball a meter above the ground, because we control that, than it is to say, I plan to shoot the ball at 3 meters per second. Because we really can't control that. That projectile launcher has a spring in it, and the spring determines how fast that thing gets launched. That's all we've got. So that we measure. Height we can control. And then there are other things that we might need to determine, but they are sort of fixed. Those are things like the acceleration of the ball once it's in free fall. We know it's going to be accelerating toward the ground at about 10 meters per second squared. And how did we determine that? Well, I just told you. How did I determine it? I mean, the same way you probably figured it out, which is you read it in a book somewhere. But ultimately, that was made by a measurement as well. Like, we measured it, and the reason that we don't have to measure it again is because it turns out that it's the same over and over and over and over and over. And if we have a value like that, then eventually we're just like, well, I don't need to measure that. I already know that that's the same. Now, that's the same way that, like, if I start the ball at a certain height above the ground, and then I tell you, like, this is 1.1 meter, we don't need to measure that every time. If we put the launcher in the same spot, it's gonna be the same height, right? Unless there's an earthquake, it's something that like changes the distance between the table and the ground. Like, you only need to measure some things really once. So these things are very general. Measurements, givens, and constants. That is not saying that every time we make a prediction in physics, we need to know the speed of the ball, the height of the launcher and the angle of launch, and acceleration of an object in free fall. Sometimes we make predictions about completely different things, and when we make predictions about different things, then we make different kinds of measurements. The information that we get with our measurements, or givens, our measurements and givens and constants, is then used to make predictions. And that's where the laws of physics come in. The laws of physics say things like, if we know that an object is accelerating at a constant rate, then we know that its final position in any one dimension is going to be related to its initial position, its initial speed, its acceleration, and the amount of time it's going to be moving. That's one of our kinematic equations. And we can go way beyond that, because we know, for example, that if an object is experiencing a constant net force, then its acceleration is going to be proportional to the size of the overall force and inversely proportional to the mass of the object. That's Newton's second law. So we can make totally different predictions with a different set of measurements if we're trying to figure out how quickly an object's motion is going to change. And then there's a whole set of relationships that we lump together in what are called conservation laws. So it turns out that under many circumstances, we can assume that if we measure something called momentum, that it's largely going to remain unchanged. Or if we measure something called energy, it will largely remain unchanged as objects move and interact. So we can expand our predictions, and we're going to be using all of these to make predictions throughout the year. And the predictions that we make depend on the measurements, which means typically what we do is we first ask, what do we want to predict? So in the case of the projectile motion lab, I am telling you that. Here's what you want to predict, and I'll go through that in just a second. In other problems, it might be different. There might be times when I ask, like, how long will it take a block of wood to slide up a ramp? And then you would be making a different set of measurements in order to make that prediction. In real life, and this is where it gets really interesting, in real life, the kinds of predictions that we need to make depend on how we're going to use them, the utility of those predictions. So I was flying around airports last night. I flew from Palm Springs to San Francisco, and then from San Francisco to Portland. And one of the things that's really interesting is when you get on the plane, they tell you when you're going to get off the plane. That's kind of neat. I mean, how do they make that prediction? Well, they make that prediction and, they have some information, right? Like, they know how fast planes can go, and they know the distance. So that's a really easy way, but it's not always the same. So what else do they use? Anybody else know what else they use when they're predicting how long it's going to take a plane? Yeah.
Every other flight on that path that they've ever taken.
Okay, so one of the things that they do is they can look at the flight path and they can find an average. But that doesn't explain how it is that if I get on the same plane, the same flight, on one day, it might say an hour and 38 minutes. The next day, it might say an hour and 26 minutes.
Wind currents?
Yeah, wind and weather. That's another huge piece, right? And airport traffic. All of that goes into making the specific prediction of when your plane is going to land. Has anybody here ever flown from Portland International Airport? Raise your hand. Okay, and have you ever taken the shuttle to the parking? How long does it take to get to the parking lot from the airport?
Depends on the shuttle.
But, let's say you're on the shuttle and you're going to the parking lot, like roughly how long?
Like 10 minutes.
5-10 minutes, right? Last night it was over 45 minutes because there was construction. Then it was late, right? So they're like, okay, this is a good time to do the construction. That's all totally reasonable. You know what would have been really nice is if the shuttle driver had said, this is gonna take 50 minutes, by the way, because I would have walked. It would have been quicker for me to walk from the airport to my car at midnight last night than it was to sit on that stupid shuttle. And those are things like, we make predictions by having information. One of the things that is like the most fascinating to me about the kind of work we can do in physics is that predictions can even work backwards. Those aren't really predictions, right? We're sort of venturing into the realm of thinking about it as answering a question or finding out information. But this is where I told you about that forensic investigator who studies like car crashes. And the kinds of questions that he is asking are things like, well, where was car A when car B turned into the roadway? How fast was car B going when these two cars like hit each other? How fast was this car going around the curve? All those kinds of questions can be answered through this process of making some measurements, applying some knowns and givens, and then using conservation laws and kinematic equations. We can largely figure out from evidence at a crash how quickly each vehicle was going. It's like, I couldn't do it, but people can do that, and they do. They work for insurance companies, and they get paid a lot of money to do that because they can potentially save the insurance company a lot of money. Anybody here, and I hope this has never happened, but if you've ever been in an accident, one of the things that leaves you most vulnerable is you realize that the other driver could potentially blame you for everything, even if it wasn't your fault, right? And this happens, like there's like, so if you are on the freeway and you're following somebody and they suddenly slam on the brakes because something happens ahead of them, somebody else slams on the brakes or somebody pulls in front of them, and you hit that car, pretty much it's your fault. It's just the way it goes. Like, you were following too close. You shouldn't have been following so closely. But if you're driving along the freeway, minding your own business, and there's nobody in front of you, and somebody pulls in front of you and then slams on the brake and you hit them, then it's not your fault. How can you prove that that happened? If you don't have like a dashboard camera or something like that, how do you prove what happened? And it's not easy. I mean, in many cases, there is no solution. I mean, that's why people have dashboard cameras, is to prove stuff like that. But you can imagine in a whole variety of situations, people just point the finger at each other and they're like, well, this was your fault. And you're looking at them thinking, no, it's not. You, like, I was driving along, minding my own business, and you literally just turned right in front of me. There was nothing I could do. I had no time to stop. And you, like, but it will look exactly the same as if that person had been making a perfectly legal, safe turn, and you'd been looking at your phone and driving like this, and you hit them. There's no way to tell. So, so being able to work backwards is a really useful skill, and we're gonna do stuff like that down the road. We're not gonna do that for projectile motion, though. What we're doing right now is we're focusing on a really kind of the basic situation in two-dimensional motion. The situation in which we have an object that's moving in free fall. So we know what its acceleration is going to be, or at least we know pretty closely what its acceleration is going to be. And we are trying to predict information about its path, where it's going to be and when it's going to be there. That's our goal. That's kind of the basic two-dimensional kinematics problem, projectile motion. There's lots of other ones, but that's our starting point. And what I'm having you all do in the lab is effectively something that you've already done in a homework problem. And this is where like the big confusion sometimes comes, because in the book, and in every book, every math book, every physics book, the problem itself starts with the first step done. That first step is the measurements and the givens, okay? So if we look at problem number 26 in the book, and I know you probably don't remember that, but we talked about it. That's the one where somebody shoots a t-shirt from one of those t-shirt guns. And we're told how fast the t-shirt comes out of the gun, 28 meters per second. We're told the angle, 40 degrees. And we know how far the t-shirt goes horizontally. It goes 60 meters horizontally. In the lab, I ask you where to put a hoop so that a ball goes through it after it's traveled a half a meter horizontally. This is the same problem. The difference between problem 26 and what we're doing in the projectile motion lab is, well, first of all, like the numbers themselves are different, right? So you can get a different numerical answer. But the biggest difference is we didn't know these things all necessarily in the projectile motion lab, and we were told all of these things in the problem. The ones that like you didn't know until the other day that your launch height was 1.1 meter. We knew in problem 26 that it was launched from the ground. You didn't know what the launch speed was until you measured it using tracker. I didn't either. That's not a known thing. Like if you look up how fast does a projectile launcher shoot a ball, there isn't one answer. It doesn't just, all projectile launchers always shoot at 3 meters per second. That's not a thing. So this is something we have to measure. In problem number 26, we are told that the t-shirt is fired with an initial speed of 28 meters per second. 28 meters. How did they know? In the book and in math books, in all the tests and all the stuff online, it always is the same way. They don't explain how that number was arrived at. We are trying to recreate real-life physics problems that sort of model these same sorts of predictions. We can't do that without knowing things like how fast the ball is going. So we had to start there. We had to figure that out first. Once we figured that out, now we can use that to make some predictions. We still need to know, by the way, the angle, because that will change the trajectory of the ball. What's the angle? Well, I told you, 20. But you all don't have, I mean, you should use 20, but I mean, you control the angle. It's not always 20. Like 20, launching things at 20 degrees isn't a like law of physics. Launch it at whatever angle you want. I picked 20 because I picked 20. There's no particular reason. It's just 20. That was fine. You all could be more general. You could say, hey, what about 30? What about 40? And in fact, in the lab, I'm asking you to think about those kinds of things, because ideally, when you come up with a set of predictions, it's something that will work for a more general case. And we'll talk more about that on Thursday, but ideally, what we would come up with is what's called a model. And a model is something that we can use to make a whole bunch of predictions. So let's talk about how this is going to play out in the lab itself. So here's what we know, and there's sort of stages to the lab, because what I want is for you to start with just one set of conditions. And that set of conditions is that the launch angle is 20 degrees from horizontal, and the height of the ball, right as it comes off the launcher, is about 1.1 meters. Okay, and these would be givens. Okay, they're givens. They're not constants, because you can put the launcher higher or lower. You can change the angle. But I'm telling you, like, let's just set it up like this so that we have an agreed height and angle. And then we know that when we fire that ball, it's going to come out of the launcher at a roughly constant speed. If we put the spring loader mechanism, you can push it in 2 clicks or just 1. But if we put it in 1 click, it seems to just come out at the same speed every time. We know that because we measured the speed. We measured it with tracker with a horizontal launch, and then a bunch of you measured it at an angled launch as well. And it just kept coming out at about the same. And that was about 3 meters per second. And so this was a measurement. This was our measurement. These 2 things are givens. And then we have one constant, which is that we're going to assume that our acceleration is 9.8 meters per second squared straight down. Okay? With those set of assumptions, we can kind of figure what this ball is gonna do. We know it's gonna kind of go like this, right? Like this is what it would do. If there were nothing in between it and the ground, it's gonna land on the ground and it's gonna follow a parabolic arc, and we can make all sorts of predictions about its vertical and horizontal motion. And one thing that I want to emphasize that we're still working on the whole vector thing. Some of you've got it nailed. You just you get it, you get the trig, you get the geometry, you get the concept of a vector quantity. And some people are still stuck in the well, what is this? Which of our variables is this? Is it the x? Is it the y? Is it? So here's how you can think about this, and I'll just kind of keep going through this because I think it's really useful. The answer is, this is the speed. This tells us how fast something is going. This, 20 degrees, is a direction. It's moving this fast in this direction relative to perfectly straight to the right. So how does that relate to axes and stuff? Well, we get to decide what axes we want to use. If we have a set of coordinate axes that look like this, where our positive directions are up and to the right, and our y-axis is vertical and our x-axis is horizontal, then this quantity right here of 3 meters per second at this 20-degree angle is not in the x direction or the y direction. If I take this axis and I put it where the ball starts, you'll see this red line is not in the direction of my x-axis or my y-axis. It's not in the direction of my positive or negative x-axis. It's not in the direction of my positive y or negative y-axis. So we don't say that this quantity right here is an x or a y quantity. To determine whether something is an x or a y quantity, or to determine when you need to break it into components, you look at the direction of that quantity compared to the direction of your x and y axes. For what we've been doing now, I've been just telling you, make your y-axis vertical, make your x-axis horizontal, positive up, positive to the right, and roll with that. The reason that you're doing that is because that's going to make this problem easiest to solve. In the future, we're going to have problems where that's not the easiest way to solve it. And I'll show you how to figure that out. You don't have to know it now. But in those problems, we might rotate our axis so that instead of the x-axis being perfectly horizontal, maybe the x-axis is angled such that it's at a 20-degree angle to horizontal. In that case, this quantity is in our positive x direction. And there's no part of this quantity that's in the y direction. So we've just changed the x and y components of this quantity because we've changed the direction of our coordinate axes. I could also make this quantity in the positive y direction. There, now it's in the positive y direction. And now it's in the negative x direction. And now it's in the negative y direction. If I use this set of reference axes, if I use this this y-axis and this x-axis, where positive x is kind of up and to the left, positive y is down and to the left, then this object's initial velocity is in the negative direction on the y-axis. And if I were to describe the initial velocities, I would say the initial x component of the velocity is 0, and the initial y component is -3. So part of understanding how to use these vectors is being able to twist your mind around that concept, which is admittedly challenging. Having said that, this is what we're going to use, and I recommend that we say that our initial position is down here. I recommend that we say that 0, 0 is located on the ground directly below where the ball is going to launch. And we work from there. But you can solve this in other ways if you want. Now, one of the things that's going to happen here is that if you were to launch this 100 times, what you would see is it doesn't actually follow the same path. When you're using the simulator, it does, because the simulator is a computer. But in real life, if we launch this again, it might go a little farther, or it might go a little shorter. It might go up a little higher, it might go down a little lower. There might be even some launches that are just weird. You might put it in the launcher and click go and it just goes boop, 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 boop. Or you might put it in and even though you only push it in one click, like the planets align and it goes farther. But by and large, what you would see, if you could like trace the path in the air, is you would see sort of a thick line that starts where the ball starts on the launcher and then kind of spreads out. It's going to be sort of a cone, right? Where most of the launches are going to sort of follow this general path. And that means that if we want to intercept the path of this ball, if we want to intercept the path of this ball, then we need to have some idea of like, well, I guess what we're really looking for is sort of the midpoint of this. Like, there's no better way to do it than to think about where on average will that ball travel, okay? And the two things that we're looking to determine are, one, where do we put a little bucket? So where do you put a bucket to catch this? Like, this isn't gonna work, and this might work sometimes, but this is gonna be our best shot. Like, that's where we want the bucket, so that the middle of that path takes us into the bucket. And where do we put a hoop vertically if horizontally it's going to be about a half a meter away from the launcher? So if this distance right here is about 0.5 meters, how high up does this hoop need to be? And one of the things that, so this is sort of your big task today, is to make that prediction. One of the things that I want you to recognize, though, is that, first of all, your initial prediction could be wrong. It might be that you think you know what the path of that projectile is going to be. And you put your bucket and your hoop in the place that you predict, but it doesn't actually follow that path. What does that tell us? Well, that tells us that our initial parameters aren't quite right. And we don't know what's wrong. The height, we can verify that pretty easily. The angle we can verify pretty easily. Those might be wrong, but probably those are okay. But the initial speed, we think it's around 3, but I don't really know. And the acceleration in the x and the y dimension, the overall acceleration and the parts of that acceleration that are perfectly vertical and perfectly horizontal, we don't know those either. We think that it's pretty close to this, but maybe it's not. Maybe it's just not. And so what that means is there's some revision that you can make, and we'll talk more about that on Thursday, once you've tested your prediction. If it works, that's pretty good. If it doesn't work, then maybe there's a way to refine your prediction so that it does work. And then the other piece is that we're changing some of the parameters as well. So once you've kind of got everything dialed in for this scenario, then what happens if you raise or lower the launcher? What happens if you change the angle of the launcher? What happens if you change the location of the hoop or the height of the bucket that it goes into? And all of those things may make a certain set of parameters work better or worse than others. So it may be that with this set of parameters, you can get it through the hoop and into the bucket. But then if I ask you, okay, now make it 0.5 meter off the ground, tilt it to 47 degrees, and use a bucket that's, twice as tall, then all of a sudden, the same numbers that worked before don't work. So how can you revise your parameters then? Because ideally, we would just have one set of parameters that was reasonably good at making predictions, right? And that's also part of what the book ignores. A big part of physics is recognizing that we are not trying to recreate reality. We're trying to come up with things that work. If I throw a ball, I want it to go where I want to throw it. I don't really care, like, if my numbers are right, as long as it gets where it's supposed to go. Same with our launcher, like, we want it to go through the hoop and into the bucket. If it turns out that fudging these numbers a little bit, that changing them a little bit gives us a better prediction, then we'll just use that, even if they're not quite right. It doesn't really matter. Right or wrong doesn't matter. It's, can we hit the target? So, so your goal today is gonna be twofold. The first is, can you make the predictions? Okay, so we've got our measurements and we've got our givens, we've got our constants, we've got all that information, our knowns are set. You've got a speed from tracker, you're gonna use the height and angle that are in the lab itself, and we can assume that the acceleration is free fall, down at 9.8 meters per second squared. Given that information, can you predict where a hoop and a bucket would go? And then the next piece, and this is going to be something that we're going to work on for a while, like months, is this larger piece of, okay, once we start testing our predictions, how can we revise the parameters that we're using to come up with a more robust model, one that will work every single time we try to make a prediction, even if we change some of those controllable parameters. So these are the skills that we're working on. And does anybody have any questions for the good of the order? I'll shut the video off.